Hello, my name is Xingfu from Argonne National Laboratory. I'm going to talk about our group effort toward an end-to-end auto-tuning framework in HPC PowerStack. This is the outline of my talk. I discuss the background and the motivations of HPC PowerStack and this work. Survey PowerStack layer-specific tuning, then propose an end-to-end auto-tuning framework. Analyze the opportunities in core tuning in two or more layers, and mention some specific use cases and solutions. I will present some research opportunities and challenges in this area, and summarize the talk and discuss some future work at the end. As we enter X-scale computing era, power and energy management have been established as key design points and constraints for any next generation of supercomputers. While there exist several individual efforts across the HPC community to research automatic techniques for managing power and energy efficiently, the majority of these techniques have been specialized to meet the needs of specific HPC center or specific optimization goals. A recent survey conducted by EEHPC Working Group concluded that the majority of such techniques lack the application awareness required to achieve the best system performance and throughput. Furthermore, each technique tends to improve management of power or energy for a different subset of the site or system hardware and at different granularities. Unfortunately, the existing techniques have not been designed to coexist simultaneously on one side and cooperate on management in a streamlined fashion. To address these gaps, the HPC community needs a holistic stack for power and energy management. The power stack started in May 2018 as a working group to gather the experience of active developers in industry, computing centers, and academia in building software interface and solutions for handling and optimizing the power and energy consumption in HPC systems in production. PowerStack defines a software stack that manages the power and energy of HPC systems and standardizes the interface between the different levels of software components in the stack. This diagram shows the current system software stack for power management from top layer side to cluster, job application, and node. Power bounds are inherited from top layers to the lower layers. We list some software for the corresponding layers, like power-aware job schedulers such as psln, PowerScale, RMAP, runtime power management, Jophin, Radix, conduct, power measurement and control interface, platform I/O, VariROM, MS-Safe. HPC PowerStack provides hierarchical design within power management ecosystem. Site-level power requirements are translated into class-level power bound, fairness, and priority requirements. By customized power-aware job scheduling, they are translated into the job-level power bound, physical node location for single job, then are translated into CPU, GPU, and DRAM power bound in the vendor-specific mechanisms. There are 4 layers: site level, system level, job application level, and the node level in the power stack. The goal of HPC PowerStack is to build software interface and solutions for handling and optimizing the power and energy consumption in HPC systems in production. There are 2 key aspects of PowerStack. One is to envision and design a holistic power and energy management software stack that could be extensible and application-aware. This enables adaptability to a wide array of programming patterns while optimizing performance and power and energy. The other is to define a standard interface to interact with optimization software and hardware knobs across different vendor HPC systems. To address this need to end-to-end optimization across different layers of PowerStack, we formed a PowerStack end-to-end auto-tuning working group in November 2019. Let's talk about overview of our working group efforts. Current existing auto-tuning is primarily layer specific. There is need to identify, quantify, and explore opportunities for cross-layer tuning. The goals of this work are to survey existing core tuning work, propose an end-to-end auto-tuning framework, identify open challenges, hard problems in core tuning, and provide a platform to drive collaboration on developing solutions. Based on the PowerStack design, there are 4 layers: site, system, job application, and node. A site has one or more systems and a power budget. Each system is constrained and a derived system-level power budget. Therefore, we focus on system, job, application, and node levels. The focus of this paper is on tuning at system, job, application, and node level. To address the following questions: the goal, metrics, parameters, and the method for each layer, and or across 2 or more layers. Describe the knobs at each layer, who controls what control knobs, can be modified at what time and space, and what to measure. Propose an end-to-end auto-tuning framework in HPC PowerStack. Identify open challenges and issues in end-to-end auto-tuning. Let's define core tuning. Tuning is the process of maximizing the target metrics through efficient handling of our available control parameters and our configuration options without violating operating constraints. The core tuning is the process of simultaneous tuning of 2 or more layers of the power stack. Typically target performance or power efficiency as the primary metric, compares with the operating power constraint imposed on the layer, and attempts to improve the management and orchestration of the available control parameters that affect application and or hardware performance. The outcome of core tuning is back to be greater than the sum of its parts. This table shows more definitions of terms like job, application, resource manager, runtime system, job malleability, job malleability, static interactions, dynamic interactions. Here I try to highlight one is job Mobility means flexibility to change the computing resource at job launch. Job malleability means flexibility to change computer resource during the runtime of the job. Let's look at a survey of PowerStack layer-centric tuning efforts. We focus on the 4 layers: system level, job level, application level, and node level. Describe the high-level objectives for the existing layer-centric tuning approaches across the different layers of the PowerStack. List the target metrics relevant to each layer. Outline the layer-specified control parameters, telemetry, and the specific method used to accomplish the objectives by the individual layers. Common objectives of each layer. Operating constraint is to operate within the power constraint assigned by our layer. Power constraints are applied and measured over a time window. The smallest supported time window is defined by what can be supported at each layer and what is acceptable by the up layer. Some secondary goals: power constraint performance optimization, performance constraint energy optimization, guarantee rate of change or lower or outbound on power, thermal constraint performance optimization, system utilization, resource utilization, job turnaround time, queuing delay, throughput. The objectives at different layers of the PowerStack can be realized using measured or derived metrics at those layers: job level power or energy usage, execution time, operating frequency, performance, power efficiency, energy efficiency, node utilization. This table shows the tunable parameters and the control and implementation methods used at each layer: system, job runtime, application, and node. This table lists the existing layer central tuning solutions and software at the resource manager job scheduler, job level runtime system, node level management, and application level tuning. We propose an end-to-end auto-tuning framework in the HPC PowerStack. A site has one or more systems, site policies, and a power budget. Each system is constrained and a derived system-level power budget. Therefore, we focus on the system, job, application, and node levels, shown in the orange boxed portion. When a HPC system is under power cap, how do we auto-tune the job, application, and node level to achieve the optimal mode solution? Based on the proposed end-to-end auto-tuning framework, we analyze the opportunity in co-tuning in PowerStack. We survey potential opportunities in collective tuning of 2 or more power management layers. The goal is to find potential area for co-tuning and prepare a list of broad research questions that we are collectively interested in tackling. Quantify, estimate gains in those areas. The expected outcome is to identify specific research activities so that the members of this working group can collaboratively partake in, depending on the area of expertise. Identify 4 co-tuning use cases. For co-tuning resource manager and runtime system, we tune the interactions based on job type. Tune the common job agnostic interactions. For co-tuning resource manager, system, software, and application, then maximize resource utilization for efficient execution through application-weighted scheduling. For core tuning runtime system software, and application, we fine-tune system software and application parameters at launch and runtime. For core tuning resource manager, with runtime system software and application, we maximize resource utilization, tune interactions, and cross-layer tuning of parameters for efficient execution. For tuning across all 4 layers, we need to carefully analyze the collective impact of each tunable parameters across layers to find the best combination for optimal performance and a power budget. In resource manager and runtime system, the objective is to explore leverage opportunities in the simultaneous tuning of the resource manager decisions with empirical or online knowledge of runtime system behavior, subject to a target power or energy efficiency metric. For interactions, we consider 2 directions of interaction, from resource manager to runtime system, and vice versa. Several types of interactions between the resource manager and the runtime system are described in this paper. Potential metrics to define the opportunity are system level energy efficiency, system level jobs throughput, tuning resource manager system software application. The objective is maximize the performance of all jobs on system and a system-wide power limit by maximizing per job power efficiency with minimum performance impact. For interactions, we quantify opportunity in tuning 2 types of interactions. Tuning the control loop in resource manager by making application characteristics where through empirical data or online monitoring, requiring changes to resource assignments by the application for further tuning control parameters within the application. Metrics, power and energy budget, number of resource, control knobs, power, frequency, concurrency control, system and application parameters. Core tuning runtime system software application. The objective is maximize performance and power cap by fine-tuning system parameters, software and application parameters at job launch and runtime. The required interface like power monitoring, CPU core and on-core frequency tuning, access to specific CPU functionalities such as MSR solve, hardware performance count monitoring, application progress monitoring, metrics like confirm, deny the configuration set assigned by runtime system, power and energy consumption, performance. Control knobs like power cap, dynamic power management, resource, the required configuration that can be applied during the runtime. Potential metrics to define the opportunity are high performance and power cap, low energy and power cap, full system utilization. End-to-end auto-tuning, resource manager, runtime system software and application. The objective is through core tuning of all 4 layers to explore opportunities to maximum application performance and power constraint, job throughput and power constraint. The interfaces are a collection of interfaces in pairwise core tuning. For example, improvement in throughput at the resource manager needs to be translated into improvement in end-to-end runtime of individual jobs managed by the job-level runtime system. This must be translated into improvements in the calculations per simulation step at the application level. Several target metrics based on the use case. This table lists the core tuning use cases from the members of our working group. A group from Argonne National Laboratory, USA, developed an auto-tuning framework to core-tune compiler application and job-level runtime to achieve the optimal performance. A group from Senegal, Unibo, Italy, developed a runtime library for performance-neutral energy saving in MPI applications to core-tune resource manager and job-level runtime to achieve the energy saving. A group from IT4I, Czech Republic, used the runtime exploration of application dynamism for energy-efficient execute computing, RADEX, to split the parallel application into regions of different resource requirements to dynamically tune hardware parameters that suit the needs of each region. A group from IT4I and Unibo plans to use two runtime libraries. One focuses on communication, the other focuses on computation to tune the application for energy saving. A group from TUM, Germany, developed a proactive power corridor management with invasive resource manager and invasive MPI to manage power using dynamic resource redistribution among applications. A group from Lawrence Livermore National Lab, USA, contains resource manager, job-level runtime system, and application to improve energy efficiency. A group from Intel developed job-level runtime power manager, Jophin, to contain resource manager and job-level runtime to achieve the optimal solution. We identify open challenges for core tuning in 4 areas: power-aware resource allocation, adaptive job tuning, reallocation, offline core tuning by selecting software components of PowerStack, online-offline core tuning on heterogeneous platform by selecting hardware components based on objectives. Core stack parameter tuning include application-level control. For power-aware resource allocation, adaptive job tuning, reallocation, how to collect cross-layer control parameters and the application parameters with power efficiency, how to quantify potential benefits of such exploration, how to incorporate application semantic information to PowerStack. For offline core tuning by selecting software components, can we quantify the impact of different compiler optimization flags for one or more target metrics on the layers of the PowerStack in the application? Can we inform the compiler toolchain about runtime situation on the cluster, including resource constraint, choice of runtime algorithm, and hardware characteristics while applying optimization techniques? Can we quantify the impact of using several variants of the application dependencies on the efficiency of the PowerStack? Can we identify correlations between black box and or white box characteristics of these dependencies and the efficiency metrics relevant to PowerStack? for online-offline code tuning by selecting hardware resource on heterogeneous system based on the objectives. How to quantify the trade-off between the number of computer devices on the system was system-level efficiency. How to quantify the trade-off between designing software approach that efficiently fewer or more computer resource was system efficiency. For cross-stack parameter tuning include application semantics. How do the existing control parameters exposed by different layers of the PowerStack and application interact with each other on scale of power efficiency? How to quantify potential benefits of such exploration? Can we extend the layer of a PowerStack to incorporate application semantic information? In this paper, we surveyed the existing code tuning work, proposed an end-to-end auto-tuning framework, identified open challenges, hard problems in code tuning. This paper took the first step in identifying and aggregating all the research and development challenges related to the interoperation among multiple layers of the PowerStack. This working group will provide a platform to drive collaboration on developing solutions. We will work on collaborative effort to develop the end-to-end auto-tuning framework and integrate the individual research activities in order to realize streamlined auto-tuning of all layers of a PowerStack. Thank you for your attention.